Good morning, welcome to new lecture. Today I will review several examples. First example, we have one column. We have pin support here. And this column is subjected to 6 kilonewton force here. And using one cable, I attach this column from point B to point C. And here again it is hinge support 4 meter, 3 meter, and this is 3 meter. So point A, B, C, D. I want to find internal force in member CB. You know, if we remove CB, what will happen? This column will rotate respect to point A like this, and it will not be in equilibrium, it will be unstable. So using this rope or cable, I keep this column in equilibrium. In order to find internal force in that cable, I can cut like this and draw free body diagram. So I will release this force FCB. Now that is tension force, and if this angle is alpha, in that case I can write FCB sine alpha. It will be component of this force in this direction, FCB sine alpha. I can take moment respect to point A, FCB sine alpha times 4 minus 6 times 7 is equal to 0. What I did, I cut this cable, and this is my free body diagram, this part. For this part of the structure, I wrote summation of moment respect to point A. Because FCB is inclined, I can project in two directions. One component will be FCB sine alpha, perpendicular to the column. Another one, it will be FCB cosine alpha. This component will not produce any moment respect to point A because it is passes through A and it will not produce any moment. But this component will produce moment respect to point A, and the distance of this component up to point A, which is perpendicular to the direction of the force, it is 4 meters. So FCB sine alpha times 4, it wants to rotate this column respect to point A counterclockwise, so positive, minus 6 times distance, 7, it wants to rotate this column respect to point A clockwise, so negative is equal to 0. Sine alpha here, it is clear in this triangle, sine alpha will be equal to 3/5, because if this is 3, this is 4, this length will be 5, the length for cable. So in that triangle we can find sine alpha is equal to 3/5. I can plug instead of sine alpha 3/5. From here I can find FCB. FCB will be equal to 17.5 kilonewton. Next example. Next one, it is one cantilever beam. It means beam with one fixed support, another side it is free. Is subjected to concentrated load at free end, 100 pound, and one concentrated moment at midspan, it is 800 pound-feet. The length for this beam, it is 5 feet, 5 feet. I want to draw moment diagram and shear diagram for this beam. First step, I will find reactions. In order to find reaction, I can find, for example, A, B, C. Summation of force in vertical direction, it will be this reaction. So AY minus 100 is equal to 0. From here, AY will be 100 pound. And in order to find reaction moment at point A, I can take moment respect to point A. So if this reaction MA, I assume it is in counterclockwise direction, in that case MA minus 800 minus 100 times 10 is equal to 0. I'm taking moment respect to point A, MA minus 800 minus 100 times 10 is equal to 0. From here, MA will be 1800 pound-feet. Now, you can draw free body diagram, and you will need two free body diagram in order to represent the behavior and draw for shear diagram and bending moment diagram. One cut should be, for example, if you assume X from this side, one cut it should be between C and B, another cut should be between B and A. So at least two cuts you will need. But without of that, I can draw with two. How I will draw that? For beam always from left to right, shear diagram. As much as reaction, I will move up, 100 up. There is no force, continue 100 down. So I will close the diagram. It will be one rectangular shape, 100 up, no force, 100 down. This will be shear force diagram. Bending moment diagram. What is the bending moment at point C? Bending moment at point C, it is 0 because it is free end. If I move from C to B side, just before B, if I cut it, what is the bending moment? It will be 100 times 5. But negative or positive, you see the positive internal bending moment direction. If I take moment respect to cut point, it will be M plus 100 times 5 is equal to 0. It will be negative 500. So it will be negative 500 at point B here. Just under B, I add another 800. So from negative 500, here it is 500. If I add another 800, it will reach to the 1300 negative. Then at point A, the moment will be equal to the reaction moment, which is 1800. So this will be bending moment diagram. Inclined line from 0, it reached to the 500, then it is jumping to the 1300, then linearly will increase to the 1800, and it is negative. And you can figure out it is negative because if you apply this load and this bending moment, this beam will bend like this. So underneath of the beam we will have contraction. So it is subjected to compression force. Compression force underneath of beam, it means negative bending moment. Of course, if you draw like me, it is good, but for exam you need to show the free body diagram and write equation. You can first, using free body diagram and writing equation, draw that, then like me you can double check to see your calculation is right or wrong. This beam, simply supported beam, subjected to two concentrated moment M, each part is L over 3, L over 3, L over 3. First step, I should find reactions A, B, for example, C, D. In order to find By, I should take moment respect to point A, for example. So it will be By times distance L minus M plus M is equal to 0. M and M, they will cancel each other, so By will be equal to 0. Now summation of force in vertical direction is equal to 0. Ay plus By, there is no any force in vertical direction equal to 0. By is 0, it means Ay is equal to 0. So this one is equal to 0 as well. Now, shear force diagram. You should draw using free body diagram. You will need at least two cuts. One between A and C, another between C and D. So you should select X in this region from 0 to L over 3. Another time you should select X between L over 3 to 2L over 3, and other side it is symmetrical. So I will not do that. You should do it and double check your solution. For beam, we can move from left. Here there is no force. So until the end there is no force. This is shear force diagram 0. Bending moment diagram. At point A, bending moment it is 0. Because it is hinge. Hinge means no resistance against bending moment. No reaction against bending moment. Bending moment, it is equal to 0. So here it is 0, point A. If I move from A to C just before C, bending moment will be Ay times L over 3. Because Ay is 0, again, this part is 0. At point C, what is the bending moment? It is M. Again, if you look at point B, there is no bending moment because it is hinged. If I move from B to D side, just before D, if I cut it, bending moment, it is By times L over 3. Because By it is 0 in this region, again it is 0. At point D, bending moment, it is M. I will attach together. This beam will deform like this. You can visualize that. So underneath of the beam, we have elongation, so it is subjected to the tension force. It is positive because tension will produce elongation. It will increase the length. Compression will produce contraction. It will decrease the length. Next one. Next one, it is this beam. It is subjected to uniform distributed load. Let's I draw even a little bit down here. Intensity of the uniform distributed load, it is W, the length is L. So if this is point A, this is point B, reaction at point B, By. If I write summation of forces in vertical direction and I put equal to 0, By, minus W times L, because By is upward, the resultant force W times L downward is equal to 0. So By will be equal to W times L. Here there is no resistance against the vertical movement, so this is zero distraction. How about moment reaction? Moment reaction here, you can assume any direction. For example, let's say assume this direction, MA. What is the MA? If I take moment respect to point B, I will have negative MA plus W times L over 2 is equal to 0. From here, MA will be equal to WL squared over 2. So this will be WL squared over 2. And because it is positive, my initial assumption about direction, it is right. I wrote summation of moments respect to point B, MA, counterclockwise, so negative, plus W times L over 2, respect to point B, it is clockwise, so positive is equal to 0. MA will be equal to WL squared over 2. Shear force diagram. From left to right, what is the force? Upward. At point A it is 0. But if I move from left to right, in each step there is a force downward. It means it will linearly increase. It will come to reach to the WL, and with WL you can close the diagram negative because you are moving down. This will be shear force diagram. Bending moment diagram. Bending moment at point B is 0 because here it is hinge, and at hinge bending moment always is 0. At point A we find it. It is WL squared over 2. And if you take with trans and rotate like this, for example, this is part of the beam. If you take with trans and rotate like this, underneath you will create tension, so it is positive bending moment. Between A and B there is a load, and it is uniform distributed load. Uniform distributed load means bending moment diagram shape should be second degree or quadratic shape. So using one curve, you should attach 0 to the W L squared over 2. So with one second degree curve, quadratic shape, you will attach 0 to the WL squared over 2. You see, the derivative of bending moment should give us the shear force. Derivative of the second degree, it will be first degree line, curve line, that is right. From point A to point B, from left to right, you see shear force is increasing, magnitude is increasing, absolute value is increasing. So the slope of this curve, it is shear force. Derivative means slope. So derivative of this curve, it is shear force. Derivative of this curve, it means shear force. Shear force magnitude is increasing, so the slope of this curve from point A to point B should increase, and it is increasing. Next one. we have this overhanging beam. Here it is subjected to concentrated load. The magnitude of load, it is 6 kilonewton. This part, it is subjected to non-uniform distributed load. The shape for this load, it is triangle. It increased from 0 to maximum value 12 kilonewton per meter. This span length, it is 6 meter. This span length, it is 3 meter. We want to find moment diagram and shear diagram for this beam. First step, you will find reaction. For example, I want to find By. How I can find By? I will take moment respect to point A. So it will be By times 6 minus 6 times 9 minus the area underneath of this will be resultant force minus 12 times 6 times half times, where is the location of the resultant force? At centroid. Centroid from this side, it will be 2 over 3 times 6. So times 2 over 3 times 6 is equal to 0. So I want to find By. I'm taking moment respect to point A. By times distance will create moment counterclockwise respect to point A, so positive. By times 6. 6 times 9 will create moment clockwise, so it is negative. Negative 6 times 9. This load will create moment respect to point A clockwise, so it is negative. But what is the magnitude of the moment? Magnitude of the moment is equal to resultant force times distance of resultant force up to point A. Resultant force, it is area underneath of this triangle. So 12 times 6 times 1 over 2, this is resultant force. Times, where is the resultant force location? It is in the centroid of triangle, so 2 over 3 times 6 from point A times distance, 2 over 3 times 6 is equal to 0. From here, I can find By. It will be 33 kilonewton. Ay. In order to find Ay, I should write summation of forces in vertical direction equal to 0. So Ay plus By upward minus 6 minus resultant force for that. It means area 12 times 6 times half is equal to 0. If you plug By 33, you will find Ay is equal to 9 kilonewton. This is about reactions. After I find reaction, I can draw shear force diagram and bending moment diagram. You should find using free body diagram. With free body diagram, you will need 2 cuts. One between A and B, another between B and C. Because function, you can define 2 functions. In order to describe the behavior, one function between A and B, another function between B and C. So 2 free body diagram, 2 cut will be enough in order to draw shear force diagram and bending moment diagram. Without of that, I can draw it. How for shear force, I will start from left side. As much as reaction, I will move up. 9 kilonewton, I will move up. Then, derivative of shear, it is external load intensity. So this is linearly increasing. Okay? So the shear force should be 1 degree higher So this should be second degree shape or curve shape or quadratic shape. So now shear force in each step will decrease and the slope of curve should increase, because the slope of that, it is the intensity of this distributed load. Distributed load from A to B, intensity is increasing, so the slope of this should increase. So using one curve, I can attach this to here. At point B, 9 upward, minus until to point B, how much downward you have force, minus area underneath of this, 12 times 6 times half downward. So at point B you will reach to the negative 27. At point B you have reaction 33 up, so you will move from here 33 up. If you move from negative 27, 33 up, you will reach to the 6 positive. Then there is no force, continue. Then 6 down. This will be shear force diagram. Here, no load, horizontal line. Here it is increasing linearly. This should decrease, curve shape or second degree or quadratic shape. Intensity is increasing, slope should increase, and at point A you have force 9 upward. From A to B, how much force you have downward? 12 times 6 times 1 over 2. The area underneath of this triangle will be resultant force, so you will reach to the negative 27. At point B you will have 33 upward, so from negative 27 you will move up 33 positive, no force, 6 down, and you will close the diagram. And bending moment. Bending moment at point A, it is hinged, it is 0. Then, where is the location of the shear force is equal to 0? You should find that. How you can find that? You can cut at x distance and show free body diagram and put shear force equal to 0. So this is 9 Vx, Nx, Mx at x distance. This height will be y, but we can find y because if you write similar triangle relation, you can write y divided by 12 is equal to x divided by 6. From here you can find y in terms of x. It will be, y will be equal to 2x. So now you can write summation of forces in vertical direction equal to 0. So 9 minus 2x, 9 minus 2x times x times half, area underneath of this, minus Vx is equal to 0. If you take Vx to other side, this will be equal to Vx. At Vx is equal to 0, you can find x. These two, they will cancel each other, so x squared equal to 9, x is equal to 3. The shear force should be 0. So if I draw this precisely, this 0 point should be at middle. Let's correct that. So it should be something like this. This is 6. So from here to here it is 3 meters. So at shear equal to 0, bending moment should be maximum. Here bending moment it is 0. This is second degree. Bending moment diagram should be 1 degree higher because the derivative of bending moment it is shear force. So if this is second degree, that should be cubic shape. So from 0 it will increase to here, and the curve it is cubic shape. Then here you pay attention, this hinge it doesn't this hinge, look at point B. Point B beam above point B, it is continuous. This behavior is different from this behavior if hinge it is between these two segments. If you put beam, if we put this hinge between two segments, in that case the beam shape will be like this. In that case the beam shape will be like this. And if you add load here, you see this part can rotate respect to this hinge and will fall down. So it will be not in equilibrium, it will be unstable. So here it is continuous. Continuous beam means internal moment here at this point should not be equal to 0. If hinge it is between two segments, in that case internal moment here at this point it is 0, means no resistance against the bending moment, no reaction. But here we have reaction against bending moment, so bending moment it is not equal to 0. If you calculate the bending moment, you can find bending moment here. In order to find bending moment there, let's look at to this side. At point C, bending moment it is 0 because it is free end. If I move from C to B, just B for B, if I cut it, what is the bending moment? 6 times 3, 18. Negative or positive, this part of the beam will bend like this. This part of the beam will bend like this. Underneath, subjected to compression. Even if you cut it, show free body diagram, positive bending moment direction is this direction, this is 6. So M, negative M minus 6 times 3 is equal to 0. So you will find negative 18. So bending moment here it is negative 18. At shear equal to 0 it is maximum, and from this point, if I point, for example, name it point D, from point D to point B it should be cubic shape. I will attack. Now what is the bending moment here? If you cut and at x is equal to the 3, at x is equal to the 3, if I show free body diagram, I cut beam x equal to 3, this is the reaction 9, because this is midpoint. If this is 12, that height should be 6. And what is the bending moment here? At x is equal to 3. What is the internal bending moment? If I take moment respect a cut point, for example point O, I will have M plus 6 times 3 times half times 1/3 of 3 minus 9 times 3 is equal to 0. So bending moment will be M, bending moment will be M minus 9 times 3, because 9 times 3 it wants to rotate this segment respect to point O clockwise, so it is negative, plus 6 times 3 times half. This will be resultant force for this triangle. Where is the resultant force location? It will be 1/3 of 3 from this side. The answer for this, M will be equal to positive 18 kilonewton meter. So here moment will be 18 positive kilonewton meter. Here negative, here is line, and from A to point B it will be cubic shape. Okay, thank you so much for watching this lecture. See you next session. Bye bye.